Thank you for the introduction, and thank you for allowing me to show my research with you. Thank you, Kevin, for introducing snow melt and snow percolation before me and make it relevant actually to you, because that's not what I'm going to do. I'm just going to show you what I do and nerd out a little bit, and you can join along in this adventure. So I've been here for 2 years and 2 more years, and we have been working on nuclear magnetic resonance of snow melt. And we have finally dialed the specifics in to finally show people some data. And we're definitely not there yet to make quantitative results, but I'm gonna show you how we play around a little bit. So I don't need to introduce you that snow melt is destructive for your community, that you already know. I don't need to tell you that rain on snow events are extremely destructive to Yellowstone last year. If we talk about trying to model those processes that we have, like rain on snow, how water percolates through the snow, how it is infiltrated in the soil and how it's running off, all these models have been put through a rigorous review by Basalt in 2019. And what they basically found out was that the timing and the amount of runoff is very much often always off. And the reason for that is one problem. The biggest problem is that energy balances in the snowpack are huge. So the ones that go in and the ones that go out have a huge number, and therefore it's difficult to pinpoint that exact point at which the snow starts to melt. And therefore it's very sensitive to this melting point. Their main findings, other than the energy fluxes, are that we do not really know how to deal with phase transitions, that we do not really know what the pore scale dynamics is of water flow in snow, and that we do not account for microstructure in these models. So it's a big challenge, and therefore we need new pore scale models and studies and new methods to actually measure this. And what do I mean by snow hydrology? And in this case, I will talk about a little bit about snow rate. So how much water do we produce when the snow is melting? The capacity, how much water can snow actually hold onto in the microstructure before it starts percolating? The wetting, so how much if snow starts to melt, it has a very small liquid layer on the ice grains, and how much does that influence your permeability? And permeability, so you have different types of snow that have different types of permeabilities. So for example, here you have new snow. It has a very homogeneous flow of water through it, because you can't see, it's just homogeneously blue here. A little bit older snow has already some preferential flow, and ripened snow like depth hoar has a large preferential flow in it. So that you already have seen with Kevin's work, these preferential flow paths are very important if you want to model this correctly. I see that some things drops off here. What I wanted to say as a note, that we often do these experiments and think that they are representative of reality, but with dye tracer we always have to be very careful with drawing conclusions, because they reduce the melting point of snow. So it might be that in reality the transition from from homogeneous flow to preferential flow might be somewhere else. Good. And microstructure plays a big role, and if you see here 3 different types of microstructures, of fresh snow, rounded grains, and depth hoar, we can already imagine that snow melt and snow percolation must be very different in these types of microstructures. So this is the research gap that I'm addressing. So we are very much in need for new methods to study pore scale dynamics of water flow and phase transitions. And we are going to propose a new method, and that is using MRI. And I have to say, maybe a little bit of a trigger warning for you guys. Magnetization of liquid water how many people have had 0 MRIs in their life? Wow. Do you also have still your ACLs in place? Good. How many have had one or more? Oh, sorry, at least one. At least one. 2? 3? 4 or more? Okay. Right, so we all have had our MRIs, and on average it's about 3 amongst the skiing community. And obviously the accidents are a cause of that. And this is what you don't want to look at, because there's no ACL in place here either. But how many of you do actually know how an MRI is working? So in our lab, it will look a little bit different, because our sample sizes are much smaller than the human body. But the main principle is that water has 2 protons, and each proton has a spin. So it has a quantum mechanical parameter that you can forget about it. But what they do is they spin in one direction, and half of the other protons spin in the other direction. So what you do is, if you apply a magnetic field to this, they'll try to start to align with that magnetic field. The ones that go counterclockwise will align with magnetic field, and the other ones will anti-align. And therefore, if there's not always add up to 0, so you always have a net magnetization here, pointed out, big M, that we want to measure, actually. But since this is very small, we tip this magnetic vector into the transverse plane. And since they were all precessing either this way or that way, when we tip them in the transverse plane, they add up. And that's why we actually can measure this magnetic resonance. And what you see, so if we tip it in the transverse plane, we give it one 90-degree pulse, that's what we call it, they will start to slowly precess back to its original magnetic field. And this is what we measure. So if you look at the signal that we can measure, it's like this precessing of this net magnetization will slowly return to its normal value. So in the initial amplitude of the signal will tell you how much water we have in our sample, and the decay will tell you something about the interactions that water molecule has had. So the decay will tell you the decoherence, so it can be impacted by flow or other types of interactions. And as any time with pulsing signals, we can measure in 2 channels, in the real and an imaginary channel, and this will give you the amplitude and a phase measurement. How we actually do measure images is that we do not have one magnetic field in the z direction, but we apply a gradient. So all those spins will precess with a slightly different frequency. And then we target the free induction currents that we can measure at every different frequency. And this is how we build up an image. This is the example of a 3-dimensional bead pack filled with a little bit of water. And I make an image of the resolution of 200 micron. Sample size is 2.5 by 3.5 centimeters. And I have 125 times 275 pixels, which is way less than the first Nokia image on your mobile phone. We measure the liquid water content, and how much time do you think this will take? So, like about a minute. Hands up.
A minute.
2 minutes. An hour. 3 hours. More than 10 hours. It's actually 12 hours. And this is because it's so small, right? If I make an image of you, if you go into the MRI, it takes a little less. It takes about half an hour or 20 minutes. But the resolution is at 1 millimeter. right? And that's a very different scale than I have to look at. So there's very much a trade-off between temporal and spatial resolutions, and therefore we have to change our game, because if we want to capture liquid water flow in snow, we have to do a different approach. So we went for 1D profiles and the resolution of 70 micron with 50 milliseconds. And this is a very simple experiment that we did. And we just had a tube filled with water, and it went into a smaller tube with a plug, and I just unplugged it so the water drained out. And this is what I measured. So here, this is the profile height, and this is the time in the x direction. And this is where you can see that the signal, the water-air interface slowly goes down, so it slowly drains. This is what I want. This on the left-hand side, we have the intensity. This tells me the saturation. And on the right-hand side, we have the phase. And in the phase, we see something incredibly interesting. Because here, I did not plug, in the very beginning, I did not plug the tube yet. But at this specific point, at 2 seconds, I unplugged it. And you see a big shift in my phase. And the phase has actually the velocity encoded. And this is interesting, because if we have a jump in the phase, we know our system is flowing. So this combination can tell us saturation and if our system is flowing. We do see that the phase is shifting at a later point. This is still, we really don't know how to deal with it yet, but we do know it has to do with two different susceptibilities of water and air. What if we do the reverse? We, instead of drain it, we imbibe it, or we put a syringe on it and we plug the water back in. Then we see something very interesting, because you see again, like the water level is increasing, but we see that just underneath the surface, we see dark spots. And this is because we have turbulence in our system. So the water bubbles up in this tube and goes up. And we see clearly this in the phase with the signature of the length scales and the time scales of our vortices in the tube. So this is for us to get to know the system a little better, right? We do know velocities influence our measurements. We do know saturation influences our measurements. So this is how we can start measuring water, so water flow in porous media. So the first thing we do is we have a tube with glass beads, and we drip water on it just to see what we get. And we see here that the water comes in, and the wetting front gradually goes down. And when we have a dark streak in the middle, we know that's the drip, right? That comes in, because we have velocity fluctuations. Velocity comes in, and these small fronts will tell you that the water after the drip is slowly moving around in the glass beads. Now we're ready for snow, right? So I'm not doing anything. I just put snow in the magnet and just wait and see what happens. So what we see is that slowly we see at different locations the liquid water appearing. So on this side we see the intensity, and this is just the variance of my intensity. So I see that where I can a little bit better see where the layers of the liquid water are. So we see slowly it is increasing, but we don't see any vertical transport, because I don't see any strikes in my image. Sometime later, the same sample, but a different time scale, so a different time, we see that the snow is slowly compacting, but also I see these vertical stripes in my difference, in my variance profile. So this is clearly a different regime, where first liquid water was going in between the grains, and now the liquid water starts to go from grain to other grains, right? So this is, yeah.
In this experiment, you're just letting the snow come up to room temperature, basically? Like,
yeah.
Gradually?
Yeah, gradually. Exactly. just snow melt. Very simple. This is an experiment where I just put a snow sample in the magnet, and I put the drip flow on it, right? So we see the drips coming in at different locations. But what is very, very different from this image than the one that I showed before is that the wetting front comes in instantly instead of gradually diverging through the porous media. And this is because of the liquid water film that is already present at all the grains. And this is very important to realize, because if you model snow as if it were sand, what modelers do, then you will miss the timing and you miss the permeability. This is also one of my favorites to look at, is where you actually see, so the snow has compacted already quite a bit, and you see the liquid droplets, the rain on snow event, quite clearly already, also when there's no snow around. So you see the liquid water coming down and hitting one time step later the snow surface and going through. So what you also can see is that we have those instances where the liquid water enters the snow. It will also coincide with small collapses of small layers. This is the opposite, where I try to imbibe the snow with liquid water from the bottom, and you see the liquid water comes up. And this is a little bit dramatic. I mean, it melts very, very fast. And you see the layers kind of very dynamically going into each other. And this is where I think what you could see in real life as well, is that snow can very quickly change from a solid matrix to a mushy type of material. And this is where I actually put a secondary flooding in, where you see a different wave coming up, where I blow up the snow and the snow is floating on top, and you see different, in the next frame, different time scales and different movements in it, where you know I have a mushy layer instead of a solid ice matrix. In conclusion, we have seen now turbulence. It's possible to measure that in my setup. We have rain on snow events, we have snow melt, we have instabilities, and with that I want to conclude. And so if you have any questions, I would like to thank Joe Seymour and Sarah Cott, the professors that work in the magnetic resonance laboratory. They have spent so much time teaching me how to use a spectrometer. And there is so much to go from here, what we can do in the future, that I will not even bother listing it. But yeah, that's it. If you have any questions. I guess it's...
Can you do this in the field at all?
Good question. Yes, you can. We have a probe that is possible to take out in the field. We haven't tried it yet to run this particular sequence because it's already challenging in the lab, but we are very hopeful that the same sequence will run on this probe as well. And we're in the next couple of months, we can try to work together with the Sub-Zero lab to try to set it up in the lab first, and then being able to get this remote probe as well in the field.
How do you control the temperature in the machine?
Yeah, that's one of the biggest challenges that we will have in the future, because now I'm just putting snow at room temperature and see what happens. That's not a very scientific way of approaching this problem. And so
Joe's tried a number of years ago doing it down in the lab. And he had trouble with vibrations from the elevator and all sorts of problems with that.
Exactly, that will be the problem that we will have with the probe as well. So it will pick up any electromagnetic signal that is out there. So we have to do some shielding, the vibrations that you said from the building.
So you have to switch your beacon off if you ever do the same thing.
I would say so, yes. Yeah. Otherwise, you'll be running it down in circles, I guess. Yeah, but for the temperature control, you're very right. So we are working on having a liquid nitrogen flow in the system.
Because I've talked to Joe quite a bit about trying to get look at the vapor phase and stuff.
I know we have tried the vapor phase in over summer, like do a 24-hour diffusion measurement. So because, as I already said, so this decay from the signal tells you something about the interactions of your signal, and diffusion is the prime example of that. And diffusion of liquid water gas molecules is such a low signal. I think we could not distinguish.
I think he was going to try to use some different gases to see if you could.
Yeah, but the different gases is a problem because you don't do the snow problem, because the diffusivity.
I knew that was an unfair question. I was just wondering if you're talking about
So as it looks right now, we measure noise. Unfortunately, because that was one of my biggest questions in life in general, like what vapor diffusion does.
I just hope you don't do it.
I know. I was hopeful too, but any other questions?
No, don't get me wrong. What you've done is quite a bit.
Yeah. So thank you for listening to. I find this amazing data, and it's going to be really cool.